Okay, so currently we have 6 students. So Bilal and Vina are not yet in. So later we will check. So this one has a record. All right, now this is chapter 2. So we need to cover these 6 things to finish this chapter 2. So we have covered continuity equation. Continuity equation link up with mass. And then last Friday we covered linear momentum equation. Today we're going to look at momentum equation, right? Moment of momentum equation. Derivation, application, we have this seen already. So hope today we can finish this one. And if we can do it, then we look into energy equation, right? Now, if you look at your tutorial question 25, 25, 26, 27, 28, 29, and 30, these are the tutorial question which is included in the linear motion, linear momentum equation. So, and the example of the answer already included in the slides. So if you go to Moodle, if you download the PowerPoint slide for last week, I already covered that one. So 25 to question 30 is exercise. So this one, we will come back to this when we have time for revision, because we are out of time to cover our content. So however, the answer is given in the PowerPoint slide. You can go ahead and look at it during your own revision time. All right, so just make a note in your tutorial, on your tutorial paper. 25 until 30, this one is under linear momentum equation, right? So this is how it works. This is how we apply the linear momentum equation. Today we're going to look at momentum and moment of momentum equation. We start with page 16, 16, and then a question 31, 31. We're going to look at momentum equation. All right. Now just a recap of this FCV, finite control volume analysis chapter. We'll cover 3 main things and then some simplification steps. So conservation of mass just means that mass is deal with mass in and out, right? And then second Newton law of motion deal with force and torque. So today we're going to look at torque, right? Last week we look at lots of things on force. Today we're going to look at torque. And these two will create some work and power in pump and turbine. This one will be in the last chapter. We're going to look at pump and turbine. So today we're going to look at torque, right? And then law of thermodynamics is more about energy. So when we come to third part, then we will have an energy equation coming in, all right? All right, now we start with question 31. We're going to start to derive our momentum or moment of momentum equation, or MOM equation. So this one deal with okay, how this equation link up with our daily engineering problems. So we know that when we have a force and axis, we have torque. Torque or moment equal to F times D, if you recall what you learned in your physics, right? So this equation relates to torque and angular momentum flow in the control volume. All right, so this fill in the blanks in question 31. So MOM equation, or moment of momentum equation, it relates two things, torques and angular momentum flow. So this one deal with angle and then torque, these two things, right? Torques, other names for torque actually is a moment. Torque is a force times distance. All right, and this is the first equation we'll look at. So copy this equation. D over dt, change of time of what? Of your velocity, density, and a partial difference of your volume. This is volume with the head in the middle. Right, equal to force. So this is if you see this form, you know that in your equation, once you have a force, it means it fall under Newton's second law of motion. Newton's second law, the second law is focused on force. So if your equation have a force, then it's fall under second Newton law. Huh? And then on the left hand side, V rho and V, this one will give you what happened in the control volume. Okay. All right. So this one is more on the velocity, particle, and this one is volume. Right. Right. This one is force. Okay. So we start to derive for question 32. We want to arrive at that very long equation. So we start with second Newton law. All right. And then there's a diagram in your hand cloud also. So let's look at this diagram. So we have 3D, three-dimensional problems. All right. So we have x-axis, y-axis, and z-axis. And then we have a very, very small particle. That's why we use the mathematical symbol del here. It's a partial difference. It's very, very small changes. So let's say we have a very, very small sample here. And this sample was located in a distance of r from the origin, r, and with the of v. So this particle moving in this direction. All right, and we have a force, right? With a force that makes this particle move, right? Because we are using second Newton law where they deal with force. So we have a force, del force, particle. So we have velocity, force, radius. The radius is a distance. All right. All right. So we start to break our second Newton law equation further. So to form a moment, we know that what is moment? Moment is force times distance. Force times distance, or you're more familiar with the F times D distance, and the distance must be perpendicular to the force. This is what form the moment, right? Distance times force. However, the distance must perpendicular to the force. So to form the equation of MOM, or moment of momentum equation, we link out the force and the distance, in this case is R, to form a moment or torque. So what you do is that you take the second Newton law equation times the R, you get the moment. You change the second Newton law equation into a momentum equation. Right? Both sides you times R. Both sides of the equation you times R. You get momentum equation. Okay. All right. So this is just an extra explanation. R, they refer to the origin. Okay. So I'll give you some time to write this equation. Let me check. Okay, we have all of you here. Bilal is here. Vina is here. Okay. Let me mark the attendance. Okay. All right. Can we move forward?
Yeah.
Yep. Okay. Just now we have a momentum equation already. So we need to recall a cross product. and differential mathematics procedure. So when we put our R inside our domain here, so it means we create a cross products. Right. However, we won't go deep what is cross product here, right? Because that's more on mathematics. So V velocity times rho times V, rho times volume, you get mass. Mass times V velocity, you get momentum. Right, mv is momentum, is what you learn in physics. All right, and then yeah, so these are the cross products that you have. So we look at our component. So R cross V rho del V, you get these products. So you get the R over the T cross V rho del V, which is your momentum, plus R times dv rho dv divided by dt. This is a differentiation equation. So when you differentiate a cross product, you get this one. Means you differentiate the first one, carry the second part, and then you differentiate this one, carry the first part. So that's why you get this one. All right. All right. So this is in your calculus chapter where you do differentiation of two entity inside domain. Right. This is a differentiation products. So if you don't understand this mathematics, go to your calculus chapter where look into differentiation on cross product. Right. All right, we know that the change of distance, with this in this case we use r, radius. The r over the t we get velocity. Right. The r over the t, rate of change of distance, is velocity. And when you get a cross product, v times v, means this one is v, this one is v, v times v, v cross v, we get 0. This is a cross product equation, right? So we combine 1, 2, 3, combine this equation, this equation, this equation. We at the end we get this equation. Okay, so on the right hand side, you will arrive at R cross the change of force. Of the particles. Now we look at very one tiny particles. That's why we use the partial difference symbol here. Okay, so we have start from second Newton law equation. We change the second Newton law of motion equation. We times the distance from the reference point, from the origin in this case, we get the momentum equation. And then we call out the differentiation in mathematics procedure. We know that we simplify this equation, dr over dt equal to our velocity. And cross product v times v, we get 0. So the first term here equals 0. So we carry forward this one into our equation that you see on the screen here. All right. And look at the next slide. So we arrive at d over dt times r cross v rho del v. This is our momentum again. V velocity times rho times our volume. We get momentum. mv again, right, equal to our force. R times del force, right, again. And just as a note, this equation valid for every particles inside our system or inside our control volume, right, in this case. So you want to know that every particle, then you integrate, then you get the total momentum inside the system. This is only look at one particles. Right? All right. So yeah, as we mentioned just now, to get a total what happened in the system, we just integrate. So we integrate this on the left hand side, integrate the left hand side term, we get the total of momentum inside the system. R distance times force or distance cross force, we get a torque or moment in the system. This is just a mathematics interpretation. Right. So on the top, this one, we refer to the individual particles. This one refer to the total, all the particle inside our control volume or inside our system. All right. So here to here should not have lots of question. It's just a mathematics model. Right. All right. Yeah, this is just a note, side note. So when we sum up all the particle, means we get what happened in the system. This is just this is what this mathematics lines mean. Okay, now we have this equation just now. All right, now what does this on the left hand side also means? Right, when you pull your dt, d over dt to outside, from integration to outside, right, is also means that in and out actually the same, just that when you pull the del, the differential equation outside, means you have a different approach in your analysis. So when you have this kind of a mathematics form, right, you can break it into order of differentiation, right? This is just an extra explanation of what happening in our question. It means that it explain what is the big D rather than the partial differential. It's just explain what we get just now, right? This is more on mathematics, right? Okay, so on the left hand side, yeah, on the equation that you write just now, d integrate r cross your momentum mv. This is v rho d volume. This one is a product of momentum, right? On the left hand side, this one is the time rate of change. We know that we have d dt is mean time rate of change or rate of something, and this one is some of our external torque acting on the system. This is a important point. It refers to the external torque acting on the system. In if you refer to the diagram, it means refer to external force acting on these particles that make this particle to either to accelerate or to turn or to move in a certain direction. All right. All right. Now this is just to recall what is cross product mean. Just a recap for your physics. So let's look at a simple torque system. So let's say you have a force with a distance. So force times radius, force times distance, right? In this case, if we use radius, force times distance, we get a torque. And we write in the mathematical forms, we write torque equal to R cross F, means R cross F, and we have a direction because these two when you times these two, it become another vector, or in this case it turned out to be a torque, a moment, and our torque have a direction and also magnitude is going out. All right. So how do we know that the direction of our torque? Right. So later we're going to explain about your torque. So if you look at this system, this diagram, R times F going anti-clockwise, and if you use your right hand, we use right hand rules, means you put your finger, put your hand in the origin, and then you follow the swing of the force from the origin, means it's anti-clockwise, means you use your right hand, and then you follow your finger. Your finger is in the anti-clockwise location, in the anti-clockwise direction. So your thumb, direction of the thumb is a torque. So your thumb is pointing up if you're following this diagram. So this is how we get our torque direction. Torque is moving up. So for our control volume, we're still in the control volume chapter. So when our control volume meet with our system, right, means our control volume hit co-incline or is the same as our system, then our torque is identical. So this is a mathematics model that define this statement, meaning momentum or torque inside the system equal to our control volume into to our momentum inside our control volume. When this equation can be used, it means that our control volume same as our system, means if you recall our previous example, we have a solid line of our system and then with a red dash. So these two entity, when they meet together, then this equation can be used. Sum of momentum inside the system will equal to what happened in the control volume. Okay, so just make a note on this equation. All right. Now, so the equation that you look at the question 32, this lengthy equation, del T in a system equal to del over del T in the control volume plus the control surface, what happened inside there. All right, so on the left hand side, this one component represent what happened in the system. Again, we are looking at momentum equation already. So we have a R. We have a R inside our equation here compared to the previous one, compared to our linear momentum. So this is a moment of momentum. Moment of momentum, MOM. So again, we have what happened in the control volume, CV denoted by our CV, and control surface denoted by CS. This equation, all right, this equation, d over dt integrate system R cross V rho dV. This one equal to CV plus CS. This one apply to our control volume, fixed control volume, and non-deforming. Non-deforming. So these three items, when you see these three items, you should able to tell that this is a Reynolds transport theorem. Okay, quite lengthy. All right. So it's what you can see on your tutorial 32. So the first two terms is actually the body of this Reynolds transport theorem. And if you define that CV plus CS equal to D over dt, integrate inside the system, R times V rho D volume, you will get Reynolds transport theorem with this one. Okay, this is a bit refresh what we know so far. So we have a few. So the first one we have moment of momentum, R times our momentum. So R times our momentum equal to our momentum in the system, R times force. And we know that when we have a system, when our system co-incline or same as our control volume, we have an identical torque between these two. Then we have a system. What happened in our system will be what happened in the control volume, right? So just now we see these two equations. We study moment of momentum equation, and then we look at a particular condition where our system co-incline with our control volume, then we can equal these two. And then we look at Reynolds transport theorem just now for fixed and non-deforming condition. Then we can write this equation out. This is the three equation that you look at just now. What you need to do is you combine these three understanding, then you will get what you see on your tutorial paper, the question 32, right? So you combine these two because on the left hand side is still the same. You pull this one equal to this one, you get what you see on the tutorial question 32. This is how it come from. So can you see that question 32 actually show you that we can derive this equation from second Newton law and then call out your understanding in torque or moment. It means we call out both sides with R, and then we call out the what happened when we have an identical system, which means our system co-incline with our control volume, and then we call out our Reynolds transport theorem for fixed control volume and non-deforming. Then we compare all the equation, we combine, we get one equation which is called moment of momentum equation. So this is how we get this equation. All right. All right, so yep. So we look at application of moment of equation again. So we have three major guidelines there with this question 33. So we have a field assumption. So we assume the flow are one-dimensional, and the speed we use average velocity when we have a uniform distribution. So what does this statement mean? It means that we always like to simplify our analysis. So it's more easier for us to consider our flow as one-dimensional in a uniform setting. Means our flow in a uniform distribution, and we use average velocity in our calculation. All right. So average velocity, most of the time in the real case, we have non-uniform, which is in last chapter we see there's a polynomial case of profile, and then we equal to the velocity, which is u average equal to u max divided by 2. That one is the equation that we see in the last few slides. Right? The second guidelines that we should follow is number 2. We only limit to steady or steady in a mean cylindrical flow means we look at when we have steady flow, then the first term in our control volume, this one, will equal to 0. Same like what we see in the linear momentum case. So for this module, we assume that we always have a steady flow. So it won't be the same when you go to work. When you work in the pipeline or you work in the realistic case. So or you do your FYP projects, we deal with flow. So again, remind yourself that in the real case, this one, they have some value here, right? So for the analysis in all our problems in final exam or either test 1, so we always assume that our control volume component equal to 0 because we have a steady flow. This one will simplify your analysis. All right. The third one, we only focus on axis of rotation. Axis of rotation. It means if you look at question 32, the moment of momentum equation, we look at R cross F. This component. Yeah? So there's a diagram under question 33. So you have a sprinkler head here. So yeah, so you have all the R times the relative flow, the velocity, and all this. So we're going to look at one example later on, how we apply this moment of momentum equation in our case. Right? So again, we have section 1, section 2, and we have a system which is represented by the solid line, and our control volume co-incline with our system is our red dot line here. So that's why we can use this equation. So you must always remind yourself how we get this equation. Right, this equation get from the 3 equations just now. So one of the equation is our control volume co-incline with our system. Then we can use this one. Okay. So this one is in a 3D case. Yeah, again, in for this section, our elevation is z-axis. So elevation is z-axis. Right. The rest we will look into the example later on. Okay. All right. Now, just a side note, for the second term inside the moment of momentum equation, MOM equation, it have a value when the flow is crossing the control surface. So it means that we have a flow coming out from our control surface. So on the diagram on the screen here, so when we have a flow coming from the nozzle here, when this flow cross our control volume, then our second term in this equation, then we have something inside here. All right. So when your flow do not come out from the control volume, means if your flow is within the control volume, this one equal to 0. Means there's no flow in and out. There's an internal flow, but there's no contribution to the environment. So, so this is just need to take note. So sometimes we will test your understanding in this equation. So maybe we will just give you some free marks or just test your understanding in section 1 in one of the question. We'll just ask you a scenario. Analyze what is the value of your momentum inside the system if the flow contained inside the control volume. The answer is 0. Yeah, so just take note. Here's some track marks or some bonus mark for you, just to test your understanding of this equation. And the statement that I say just now, you cannot find in any textbook. All right. All right. Now just also recap what is cross vector about? So we have a velocity here and the r here. Velocity cross r with this 90 degree. Just now the diagram that you see in the question 32 just now is a force. Now we look at velocity. So when your distance r and velocity vector is 90 degree, the cross products, you take the v cross r, you get 0. Meaning when your velocity is perpendicular to the axis, in this case in your axis x, if it is 90 degree to axis x or y, in this case your cross product v cross r, you get in this direction. V going up, going to y direction, for example. So v cross r, the products will go to x-axis, along x-axis. The product of this one equal to 0. So this is just a remark. What happens if your velocity is perpendicular to the axis? All right. So this is a simplification concept. So you need to look at a question. If your velocity is along z-axis and your r is along y-axis, your product is 0. All right. The product of your v cross v, r cross v, velocity here. Again, we look at velocity, not force. We look at velocity in this case. R cross v, we get 0. This is just what I mentioned just now. We're going to always use right-hand rules when we analyze MOM equation, moment of momentum. So we're going to use right-hand rules conversion. So this diagram gives you the torque direction. Just now I show you a little bit. It means this is your force times r. You get a rotation direction. In this case is an anti-clockwise direction, and your thumb is showing the torque direction, right? And this diagram on the left-hand side. So when you open your finger, open your hand, and then you do like a gun, machine gun, or a gun position. Your index finger represent the r. Your middle finger represent the velocity. So when these two vector, or not vector, these two entity is 90 degree, you will get the cross product r cross v, right? R cross v. Means the end product is going this direction. So you compare this diagram to our axis here, simulated axis here. So if you put your finger, your index finger along this direction, all right, meaning your palm is facing outside, and then your velocity is pointing up, right, pointing up. Then you'll get your thumb is pointing towards the shown direction. Okay, this is just a revisit of your physics on vector. All right. This right-hand rules conversion is important when come to question that asks you to explain what happened when you have this kind of scenario. Means either the hose will swing to which direction. So you need to explain using right-hand rules. Okay. So on the third part there, question 33 there, a vector relationship, we still need to call out the vector relationship. V equal to W plus U. We've seen it in our aircraft engine question, right? You've seen this one before already. So V absolute, W relative, U is our reference relative to a fixed control surface. This is our vector equation. All right, so if you look at our MOM equation, so every time we have a n hat here, meaning this term can be positive or negative, depends on our direction. So just a side note on positive, negative. When the flow is in, we get a negative. The product will be negative. Again, this is the same concept as we learned in our linear momentum section. When our flow into our control volume, then we have negative. Out, then we have a positive because of the n component. Just make a side note, v dot n hat. So when your flow is flow in to a control volume, you get negative. When your flow out, you get positive. Okay. All right, now this is an application for equation to look at a sprinkler head, which is referred to the diagram under question 33. Item number 3, there's a sprinkler head diagram. So this equation apply to these problems. So on the left-hand side, we have our axle component. All right. And then on the right-hand side, we have the mathematical model. We take our R2, which is this one, the distance from the origin of the axis, R2, V, angular velocity. I cannot use the angular velocity term. It should be a velocity that theta 2 means is angular speed, right? Speed that change in the angle, in a certain angle. That's why we use a subnote theta 2 here. 2 means section 2. This is our section 2. Section 1, section 2 times our m dot. M dot is positive. Why negative sign here? Because the flow is coming R2 negative. Yeah. So this is the notes for why sometimes we use positive and negative. So if your v sub theta, which is our velocity that absolute velocity that come out from our nozzle here, if our v and our u in the same direction, then we use positive. If our v and u is opposite, then we use negative. Now in this case, we have a negative scenario. So if you on this sprinkler, the velocity will, the float will come out from this end of section 2. The direction of the float or water will spray out. So our absolute velocity will be coming this direction. However, if you sit at our U2, if you sit at this location and you look at this nozzle will move anti-clockwise. All right, if you sit at this location, you look at the nozzle head here. The nozzle head will move anti-clockwise when the water come up from the nozzle. So our U2 going this direction. How we find the of our reference U2, we take the R times our angular rotation, R times our omega. All right. Now, important for this positive and negative sign here, when you study problems, right? When you apply the MOM equation. Again, so I explain why we get negative or positive. When your V and U, the vector, these two vector, U and V, same direction, we get positive. When U and V get opposite direction, we get negative. In this case, we have a negative direction. How we explain the negative and positive is that you look at the scenario. So in this case, when your water spray out from the head here, nozzle here, your fluid flow out with the velocity V angle 2, theta 2 in this direction, come up from the end of the section 2 in this direction. However, for U2, if you sit at the reference point here and you look at the nozzle head, because of the reaction of the flowing out, the sprinkler will move backward. The sprinkler head will swing anti-clockwise, and your U2 will be opposite of your V2. So when you have a opposite between these two vectors, then you get a negative sign. If these two will go align in the same direction, then you get a positive sign in the equation. Okay, so this is on the Excel component. All right. The word Excel. So it means this is Z. This is, for example, I use X. This is Y. So if anything that swing along XY plane is called Excel plane. All right. If any movement that swing along the XY plane, it's called Excel plane. All right, this is on a 3D case. You are now at question 34 already. So he asks you to explain why negative there, and then so your shaft, the top of the shaft, when it's positive, when we have a positive sign, means we have a same direction of a rotation. So we have we know that our rotation sprinkler, if we have a system like this, so our flow will flow out like that, and our sprinkler head will move anti-clockwise, will swing like that. So if our P same with our rotational direction, we have a positive sign for our torque on the left hand side. R cross F, we get a torque in the axial plane. Then we have a positive torque. Okay. We have seen these two just now. So this term is on in our MOM equation. We have 1, 2, 3. So we explain about the first term. When our flow is steady, so first term equals 0. And then we explain how we convert our second term here according to the direction of our vector. So this term will give us R times V times m dot. So when our direction is opposite between U and V, then we get negative. When our flow is our m dot flow out, we get positive. Right, m dot, we get positive. And then our torque sign also. For our third term here, it represents our torque. So if our torque same with the direction of our rotation, we get positive for this term. Right. So in these two equations, we know that our torque equal to negative R times our m dot. This is how we get this equation. Right? So this one, we get this one, you get this one. You compare this with two equations, you get your momentum shaft equation. T shaft equal to negative RV times your mass flow rate. Right, this is what we already explained just now. Right, the second equation that you see on the tutorial sheet, question 34, the second equation, we're going to derive this equation. So we know that power is a change of work. W dot means change of work. We get power. Work divided by time, we get power. So how we get shaft power? Shaft power equal to torque times angular rotation. W dot is a power again. W dot change of work with terms of work equal our torque or moment times our angular velocity. So replace what you learned just now on the top here. Right, you substitute the torque equation. Torque equal to negative RV times your m dot. So at the end, you arrive at this equation. So we know that our U2, U equal to R times omega. So we simplify our equation to negative U2. R times omega, you get U. All right. Just recall our vector, we have V, we have W, we have U. We have three kinds of velocity vector here. When we look at shaft power or shaft, we deal with U component. We deal with U component. Be careful on that. And sometimes the equation will be defined in a term of work per unit mass. Work per unit mass means you take your power divided by your mass, right? Mass dot. Shaft work per unit mass, you take your power divided by m dot. Means both of these you take out the time entity. All right. This one is dw over dt divided by mass over dt. Right, you can take dm over dt, take out this two term away. All right. you get your work per unit mass. Right. So at the end, if the question asks you to find shaft work in the unit per unit mass, then you use this equation. Small w, shaft, is mean represent to the shaft work, equal to negative u times v vector. Right, and this one, if you can see, we use a subnode of 2 represent our outlet, or section 2 work only. Why we refer to section 2 only? Because we are referring to moment. Moment, how we get moment or torque? F times distance in your physics, or in this case, we use R. F cross R, we get torque. So in this case, if you look at here, you only have torque when you have a distance from a reference. So that's why we only look at section 2 rather than at the origin. Origin, we don't have any torque here because our R equal to 0. When you cross something with 0, you get 0. Right, this is just fundamental for physics. So again, why I already explained why we only look at section 2 and not section 1. All right, just a note at question 34, we get a negative sign there. When we have negative sign, it means that the work is out of the CV. Shaft work out of CV. Or another term, another explanation you can do is that the work is done by the float on the object itself. Means the float is doing some work when you get negative. Why? Because this equation referring to the shaft. So you have a negative sign means the shaft is not doing work. And where does the work come from? It comes from the float itself. So this one you need to understand what happened when you have a negative sign. And again, since we have an online exam, we will test most of your understanding with all this area. What happens if you get a negative in your answer? You need to explain. All right. All right, I think we have a short break after we cover lots of equation from question 31 up to question 34. Okay, let me stop the recording.